Hi, my name is Nurin Akila binti Muhammad Razif and my matrix number is BC252013. So for the first question, I will be explaining an algorithm to find a spanning tree. So what is a spanning tree? A spanning tree is a subgraph that contains all the vertices of a graph. In a spanning tree, all vertices remain connected and has no cycle. A spanning tree with n vertices will have n-1 edges. There are two algorithms to find a spanning tree. First is depth first search (DFS) and breadth first search (BFS). So here we will focus on breadth first search (BFS). BFS is a graph traversal algorithm that explores vertices in a level-by-level manner. BFS is commonly implemented using a queue data structure, which follows the first in, first out principle. So the steps are: first, we will select a starting vertex and mark it as visited. Insert the vertex into a queue. Then while the queue is not empty, remove all the front vertex, examine all adjacent vertices, mark unvisited vertices, and add them to the queue. The process will continue until the queue is empty. So we will take a look at example here. So starting from A, the queue will be A. So then we will remove A, add neighbors D, B, and D. Then the queue will be B and D. Then we will remove B, add neighbors C while the queue is C and D. Then we remove D, so it will be no new neighbors, so the queue will be only C. Then lastly, we will remove C. It will be done and the queue is empty. So here the visit order is A to B to D and C. The mathematical formula involved is E equals to n-1. E will represent the number of edges and n represent the number of vertices. Second one is n to the power of n-2. It is a Cayley's formula to calculate the number of distinct possible spanning tree.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nodamia Batrisha. My matrix number is 251501. So for this part, I will be talking about tree data structure. First, let's talk about BST, which is binary search tree. So a binary search tree is the type of binary tree where each node has two children at most, which are the left and the right children. So the main rule of BST is the right children must have a smaller value than the roots, while the right children must have a bigger value than the roots. So because of this rule, searching, inserting, or even deleting data can be done more efficiently. So with an average time of complexity of 0 in parentheses log n. BST also is a dynamic structure, which means that it can grow as we add new data. So once we add one new data, it will automatically organize itself based on the BST rule. And the outcome of this sorting method, the data will come out in an order, which means that it will sort, for example, as descending order or ascending order. So there are two types of BST tree. So let's talk about the first one, which is the balanced tree. So a balanced tree is a tree where the height difference between the left and the right subtrees is more, and usually not more than 1. So this means that the trees grow evenly on both sides, and it doesn't become too tall on one side only. So because of this operation like deletion, inserting, or even searching will stay efficient. Example of a balanced tree that I can see here is like AVL tree or red black tree. So in short, a balanced tree keeps the tree short and wide, which make it fast to find one specific data. So on our right, there will be an unbalanced tree. So as we can see here, an unbalanced tree is a tree where one side is much deeper than the other. We can see here that the tree is grow heavily only on the right side. And this usually happens when we insert the data in bad order. For example, we inserting sorted data like 10, 20, 30, 40, and 100 here. So the tree will look like a link instead of a proper tree. So in this case, operation will become slow, which its time complexity will go to 0 in parentheses n. So an unbalanced tree will become tall and skinny, which affected the efficiency of using BST as a sort method. Okay, now let's talk about max heap. A heap is also a binary tree, but it follows a different rule, which called heap property. So in a max heap, the parent is always have greater value or equals than the children. So we can say here that the largest value will always be on the top. So heap is also a complete binary tree, which means that all levels are filled except possibly the last one, and the last level is filled starting from the left to the right side. heap also can be said as a dynamic structure. Why do I say so? It is because when we insert a data or element, it will reorganize itself using shift up or shift down to maintain the heap property, which means that in order to maintain a larger value to always be on the top, so there will be a movement in terms of shifting upward or downward. So I can see here that the main advantage of using heap is that getting the maximum value is much more faster if we compare to BST. So for this part, I will show you how heap property works. So from here, we can see that there are structure here. As I mentioned, that heap property means that the top value will always have the largest value. So here, the root of this structure is 50. And then down here, we have 30, 40, 10, 20, and 35. So what happened if we say that we want to add one new element, for example, 5. So as I mentioned, heap property will sort their data from left to the right side. So as we see here, this structure have one free space which doesn't have its chart. So if we look back at the property, it's stated that the sorting method must always start from the left side. However, for this case, we can see here that the left side is already filled up, and the only space have left is this side, which is the right side. So let's put the 5 here. Okay, so I've mentioned that heap property also have a process where there will be shifting up and shifting down. So let's say we add new data here. So 5 will be placed here. So we need to compare this new value with the root, with the parents. So the parents of 5 is 40. Is 40 larger than 5? Yes. So there will be no shifting down and shifting upward, because 40 is already the largest value in this subtree.
Next, I will explain about sorting algorithms that utilize tree. Before explaining about the examples, sorting algorithms is a method used to arrange data in a specific order. Some sorting algorithms use tree data structure as a tool to organize and sort data efficiently. For the first example of sorting algorithm is tree sort. Tree sort is comparison-based sorting algorithm. It uses binary search tree, which is BST. Elements are inserted into the BST, and the sorting is obtained through tree traversal. Next is the role of tree in tree sort. So for the first one is BST stores data in a structured manner. Second, tree structure helps produce sorted output. And third, improve organization of data during sorting. So for the second sorting algorithm is heap sort. Heap sort is comparison-based sorting algorithm. It uses heap tree, which is heap max. Heap is built from the data elements, and sorting is done by repeatedly removing the root. Next is the role of tree in heap sort. So for the first one, heap tree keeps the largest element. Heap tree keeps the largest element at the root. Second, tree structure maintains ordering during sorting, and the third one makes it efficient to find the maximum value.
As for the real-world example of a tree data structure, we chose a game-level system. In many games, players start at a single point and progress through different levels based on the choices they make, and this structure can be represented using a tree data structure. So, what is actually a game-level system? A game-level system is a game structure that is divided into different levels and where players need to make choices during the game, and each choice they make will lead to a different level or a different ending. On this slide, we have included a simple tree diagram clip art to represent the game structure and its element. The base of tree represents the root node, which is the starting point of the game, and each branching point in the diagram represents the node where the player makes a decision and moves to a different level. And as for the end of the branches are known as leaf nodes, which represent the final outcomes or endings of the game. This structure forms a tree because it is hierarchical and does not contain any cycle, and the player cannot return to a previous level using the same path. So this is the tree diagram of game levels that we have done, and this is the starting of the game, which is the root, and then we move to the level 1, and we have two different choices, which is level 2A with the ending A and level 2B with an ending B. And lastly, the advantages of using tree structure in games are it makes the game flow easier to manage and also support multiple endings and also allows new level to be added more easily.
Moving on to the last part of this topic, which is limitation or challenges. My name is Nazifa Binti Nazim. My metric number is BC250746. For this topic, there are two limitations, which is the first one is how binary search tree could degrade performance, and the second one is why spanning trees can be fragile in network design. As you can see here, this is the efficient structure of binary search tree. Because what? Because it is balanced. As you can see here, from node 1 until 7, the height is just 3. 1, 2, and 3. So for searching any value between 1 until 7, the searching value is at most 3 comparisons. So that's very efficient because it only takes O log n time. And this is why binary search trees are so powerful, but when they are balanced. But what if they are not balanced? So here's the problem. Let's say we have sorted data like 1 until 7. So as you can see here, the tree does not branch. Instead of being tree, it looked like a linked list. Now, as you can see here, the height is now 7, which is equal to the number of roots. And this is what we call as degenerate tree, because the tree does not branch. Now, let's start searching for the value of 5 by compare between these two structures. As you can see here, on the left side, we have balance, right? So in the balanced tree, it only takes 3 steps to find 5, which is the first one is 4, and then 6, and then 5. The time complexity is O log n, which is very efficient. But on the right side, which is the unbalanced one, it is much slower. We have to go through from 1 until 5, which is we got 5 steps in total. So the time complexity is On, which is quite slower from the balanced one. So let's say if the tree has 1000 nodes, this difference becomes huge, about 10 operations versus 1000 operations. So that's roughly 100 times slower. So if you ask me, is there any solution to this limitation? And my answer is yes. For binary search tree, we use a self-balancing tree, which is AVL trees and also red-black trees. As you can see here, after every insertion or deletion, these trees automatically rebalance themselves after using rotations, so they never become skewed. And because of that, their height stays low, and all operations like search, insert, and delete, they are all guaranteed to run in O log n time, no matter how the insertion order are. And this is why self-balancing trees are used in real system. For example, like Java's tree map and also std C++, so which is implemented using red-black tree. Now, let us take a look at the next one, which is the spanning tree. So, a minimum spanning tree gives us the cheapest way to connect all nodes, like designing a road network between cities, like how I show on the screen here. Here's an minimum spanning tree connecting all 5 cities with minimal cost, all cities can reach each other. But here's the critical limitation. By the definition of spanning tree itself, meaning that they have no cycles. So, meaning that between all of these 2 cities, there must exactly only one path. So, let's say if just one road fails, like this connection between D and E city, the entire network splits into 2 disconnected parts. So city E becomes completely isolated than the other cities. So this is called as single point of failure. So what's the real world implication of this fragility? Let's take a look at this comparison. On the left side, we have the theoretical minimum spanning tree, which is clean and minimal, the absolute cheapest way to connect all the nodes. And on the right side, we have a real network, which is, you can see the differences. This one has extra connections, so it has multiple paths between nodes. This is not really a problem to solve in theory. It is a fundamental trade-off.
A minimum spanning tree gives us the cheapest connected network by definition. The no-cycle property that makes them cheap also makes them fragile. So in practice, engineers will face this design choice, whether they want to accept this fragility or not, or they would like to pay more for redundancy. To summarize all of this trees presentation, trees have two critical limitations we must understand. So the first one is unbalanced binary search tree could degrade performance with sorted data, but we can solve it by self-balancing tree, like AVL trees and also the red flag trees one. And the second one is spanning trees are inherently fragile due to their no-cycle property. This is not a problem to fix in theory, but it is more a fundamental design trade-off between minimal cost and reliability. Together, this limitation teaches us that theoretical optimality does not always mean practical usability. Real-world systems often need balanced tree for performance and redundant connections for reliability. And understanding these limitations could help us choose the right data structure and design it much more better. That's all. Thank you.